Hey there everyone, Mr. D here, and in this video we're going to be kicking off Unit 2, talking about relations and functions, and how to handle function notation, and what does it even mean to be a function. Just as a heads up, today is going to feature a whole lot of vocab, and for that I'm sorry, I'm not normally a huge fan of words, hence I'm a math teacher. But if at any point you need to pause the video, please feel free to do so, because we have a whole bunch of text and visuals that we'll be covering. So I'm not going to expect you to kind of be able to keep up writing as the video goes on. So without further ado, let's begin, shall we? So first, as promised, vocab, yay! First, let's talk about relations. A relation is just any set of ordered pairs. Typically, we will see these as x comma y values. Your domain is going to represent your x values. So domain is always going to be your input. Your range will always be the y values or your output. So here I have some examples. We're talking about ordered pairs. My domain would be all of the x values. So -3, 3, 4. You'll notice the same, you can't really see the highlight, but same domain values here, same domain values here. My x values, if I were to plot a little dot on the x-axis, where all those points are, would still be -3, 3, and 4. My range, similarly, would be 4, -1, and 3, and that will hold true no matter what type of scenario we are dealing with, whether it is a table, a set of ordered pairs, a graph, or a mapping diagram. We'll see these occasionally in this class. You'll see them on some of the assignments, but just as a heads up, there's really not a whole lot of usefulness in the mapping diagrams in the lower level math classes. Once you get into advanced collegiate level stuff, those will show up, but that's not for a long ways away. All right, so now we know what relations are. Let's go ahead and see if we can make sense of a scenario. Here we have the average water temp in the Gulf of Mexico in Key West, Florida, varies during the year. In January, the average water temp is 68. That would be awesome. 68 degrees in January, dang. February, 70 degrees, March, 75, and in April, it is 78. Let's represent this in 4 different ways. Well, you'll notice here we have the ordered pairs, the mapping, the tables, and our domain values are going to be 1, 2, 3, 4 to represent January, February, March, April. So just the months, right? And then the range values, no matter how we represent it, that's going to represent the actual temperatures because the months determine the temperature. So it's asking, what is the domain of this relation? Well, the domain here is going to be 1, 2, 3, and 4. Now when we write this out, we're going to have each one of these numbers separated by a comma because it's going to be a list. And to denote this as a list, we're going to use some notation. We're going to actually use braces. So the domain equals 1, 2, 3, and 4. Now for the range, we have our y values, 68, 70, 75, 78. 68, 70, 75, 78. 68, 70, 75. Oh, there we go. Separated by commas and using braces to denote, and I'll say R equals for range. All right, so now we have domain and range taken care of for relations. Well, now let's talk about what does it mean to be a function. Again, if you need to pause, feel free. A function is a special scenario in which each element of the domain, aka the x values, corresponds to exactly one element of the range, aka y values. So each x only gets one single y, aka you'll never see your x values paired up with 2 separate y values. So we want to know, are the following scenarios functions? So do the x's repeat or no? Well, I'm noticing here, if I look at my x values, 4, 8, 1, 6, and 4, I'm noticing 4 shows up 2 times and with 2 separate y values. So that's a huge red flag for me. So no, this first one is not going to be a function because you can't have those repeated values. This second one here, if I were to think of this as ordered pairs, we'd have -3, -2, 0, 7, and then 4, 1. I'm not seeing anything repeat there, so I'd say we're good. That could be a function since there's no repeated x values. Next example, I'm looking at the x's, not seeing anything repeat, therefore it is a function. Last one here, I'm noticing, hey, we've got 2 arrows spitting out of that input value of 2. So I've got one element of the domain going to 2 separate range values. That's not going to be allowed. That's big fat no can do'sville. Therefore, not a function. So now let's say real world scenarios. Is it a function or no? First one, person's height to their age. So if I were to relate height, let's say in inches, to age in, let's say, years, would that be a function? No, because many people are the same height, right? There's several 17-year-olds out there who are 6 feet tall or 5'7". So it's not like everyone's height is unique to a given age or vice versa. Person's driver's license to their name. Yeah, that would be a function, right? Each individual driver's license number goes to one specific identity. At least I hope so, unless my identity got stolen. Jersey number to NFL athletes. Well, no, because several athletes wear the number 10 or the number 11 or 17. So those numbers are not unique to individuals. Now, graphically, we can tell if a graph is a function if it passes what's called the vertical line test. And the vertical line test is when you're able to take a vertical line, or kind of like your pencil, and drag it across the graph. And if at any point your line intersects with that graph at more than one spot, so 2 points, 3 points, right here it's intersecting at 2 separate points, then it's not going to be a function because we'd have one specific x value, right? If I think of this on the x-axis, we'd have 2 separate y values that corresponded to that one individual x value. So it would fail the vertical line test. It's not going to be a function. So I want to know, are these scenarios here representative of functions? Well, if I drag a vertical line across, no, not quite. Right? I've got 2 intersection points, boom and boom. Therefore, not going to be a function for that first one. If I go to B, that's good. That's good. It's not hitting at 2 separate points, so I think we're good. B checks out. Do the same thing now for C, and it's only intersecting once across that vertical line. So the first one was a no. The second 2 were both yeses. Awesome. Now let's get into function notation. This shows up all the time in upper level math courses and physics courses as well, because everyone knows physics is just the science version of math. So it's important that we know what functions are saying and how to read them. So a function rule is just a way to generate lists of ordered pairs, right? To put in an input and get an output out of it. This is probably the notation that many of us are used to, where we have y equals mx plus b, right? That's the most user-friendly. We've been using that for years, and it's treated us great. Now what we need to do is start getting used to function notation. So this little f parenthesis x, this is not f times x. This whole piece is actually one entire unit, and it is read as f of x. So this little phrase right here is f of x, which means this would be f of 1. Now whatever the value inside the parentheses is, that's going to represent what is getting replaced as an input. So over here, when it says f of 1, that means we're plugging 1 in for my function. Whatever we're plugging in, most likely x, that's going to be your your independent variable. And whatever we're solving for after we've plugged our input in, that's going to be our independent. Backwards on that, our dependent variable. All right, so let's get some practice here. I've got f of x equals -3 times x squared plus 1. So whatever is in the parentheses here has to get plugged in for the x. So what that means is I'm going to be taking -3 times whatever my input is squared. I'm going to add 1, and then that's going to equal some value. All right, so let me shrink this little bit down. Oh, boy. I don't know if I can shrink that down. All right, I digress. So for the first example, it says I'm plugging in -3 for x. So if I plugged in -3 here, -3 squared is a +9. So -3 times +9 is -27. Plus 1, I'm at -26. -26 for the first one. Second one's going to be a little bit troublesome because I've got -3 times x plus 2 quantity squared plus 1. So I need to figure out first, what is x plus 2 quantity squared? What does that shape out to be? Well, x plus 2 quantity squared, that's x plus 2 times another x plus 2. So if I did some distribution, or if you guys learned it as foiling, whatever, I would get x squared plus 4x plus 4. So this is really saying -3 times x squared plus 4x plus 4, and then add 1. So this is really saying -3 times this whole mess of x squared plus 4x plus 4, running out of space, plus 1 at the end. When I do all of that, I will get -3x squared minus 12x minus 11. All right, and then our last one here, 3 times f of 2x. All right, well, first I need to plug in 2x for my function, but there's also this 3 that's kind of hanging out. So I'm going to set that off to the side and kind of ignore it to start, but it will come into play. So I'm going to have 3 times -3 times 2x, quantity squared, plus 1. You'll notice here I'm using brackets just to denote that it's a separate type of parenthesis, but it's going to behave the same. All right, well, 2x squared, since there's no pluses or minus inside the parentheses, that squared affects both aspects. So 2 squared is 4, x squared, well, that's just x squared. So this is going to be -3 times 4x squared plus 1, so -12x squared plus 1. But don't forget, we have to multiply that whole thing by 3 because this guy was coming along for the ride. So when we do that, we will get -36 x squared plus 3. That was kind of a gross one, huh? All right, now on to some word probs. We're in the home stretch, folks. In the home stretch. Again, if you need to pause it, feel free. All right, we have tickets to a concert are available online for $35 each, plus a handling fee of $250. The total cost is a function of the number of tickets bought. Write a function rule that models the cost of concert tickets. Evaluate the function for 4 tickets. So this one's got 2 parts to it. First, we have to write a function rule, and then we have to evaluate that function rule. As we're going through and doing these, we want to make sure that we are identifying what our independent and dependent quantities are going to be. Well, for this one, my independent quantity is going to be the number of tickets, and then the dependent will be the total cost, because cost depends on how many tickets you buy. I could write this as f of x. That's totally legal. Absolutely nothing wrong with that. However, given the nature of this problem, I think it might actually be easier for someone to just kind of pick it up and read it if I wrote this as, let's say, cost as a function of tickets. So this would be read as C of t. Now, when I'm writing my function, it's $35 per ticket, and then handling fee of $250. So 35 per ticket, all tickets were represented with T, plus 2.5 to represent that handling fee. Little side note, be careful when you're writing T's, because sometimes they can look like pluses. That's why you'll notice I always put a little tail at the end of mine. All right, then the part 2 of this says evaluate the function for 4 tickets. Okay, so I'm finding what is C of 4. What is the cost of 4 tickets? So I'm plugging in 4 for T right there. So 35 times 4 is going to be 140 plus 2.5. Well, that would be 142.50. All right, next one. You're buying bottles of a sports drink for a softball team. Each bottle costs $1.19. Write a function rule that models the total cost of a purchase. So I've got cost and bottles. I'm going to go ahead and write this as C of B. Cost of bottles. And it looks like it's going to be pretty straightforward. $1.19 per bottle, so 1.19 times B. And then it's asking what is the cost of 15 bottles? So it's going to be what is the cost of 15? So I need to know what is $1.19. That's a nasty 19. Ugh, I'm sorry. So I'm just going to plug in 15 for my variable. So the cost of 15 bottles is going to be $1.19 times 15, which is $17.85. All right, last and final one. You're going to rent a car from 2 different rental companies. Proxy Car Rental charges 32 cents per mile plus an $18 surcharge. And Your Pal Rental charges 36 cents per mile plus a $12 surcharge. So we need to do a function rule for each of these. Let's go proxy. I'll say P of X, or P of M, because it depends on miles. So P of M, and that's going to be 32 cents per mile plus $18. And then Your Pal, I'll say Y of M equals 36.36 M plus a $12 surcharge. Which company offers the better deal for an 820-mile trip? Well, they're telling me, hey, plug in 820 for M and see what you get. So if I were to plug in 820 for M there, what would I get? So 0.32 times 820 plus 18. That would give me 280 and 40 cents. If I did the same thing here, if I plugged in 820 for M on the Your Pal deal, that would be 0.36 times 820 plus 12. That would be 307 $820. So clearly, this is going to be our better deal for 820 miles. All right, folks, that is it for this lesson. Sorry it was kind of lengthy, but as you can see, we did cover quite a bit. Your homework tonight or today or whatever day you're watching this video is going to be the day one assignment. A lot of it is going to be these style of questions, so that homework assignment should go by extremely quickly. But if at any point you have any questions, please let me know. And you know the drill, folks. Good luck. Have fun. Be safe. Roll Tide.